So now that we have defined the sine and cosine functions in terms of the coordinates of a point on the unit circle, let's learn a little bit more about the unit circle. And I'm going to remind us that for a point on the unit circle, the x and y coordinates, the x coordinate is the cosine of the angle, and the y coordinate, is the sine of the angle theta. So here we have our unit circle, and there are a few important or well-known angles that we're going to use. So we're going to look at this angle right here, and I'm just going to put it in radians to get us more used to radians. So this is the angle pi over 6, and this is the angle pi over 4. This is the angle pi over 3, and then all the way around, not all the way around, but the quarter circle is pi over 2. We call the positive x and y quarter of the xy plane the first quadrant. So we are going to just look at the first quadrant first. And we already know a few coordinates of points on the unit circle. Since the radius is 1, this point over here on the far right has x coordinate 1 and y coordinate 0. And that gives us two values that we are looking for. It tells us what the sine and what the cosine of 0 radians are when our angle is 0. So it tells us that the cosine of 0 is 1 and that the sine of 0 is 0. So this point right here tells us that the cosine of 0 degrees is 1 and that the sine of 0, sorry, let me fix that. The cosine of 0 is 1 and the sine of 0 is 0. Similarly, the point at the top has x coordinate 0 and y coordinate 1. So that point tells us that the cosine of the angle pi over 2 is equal to 0 and the sine of pi over 2 is equal to 1. So we can fill that in, pi over 2 over here. So we have 0 as the cosine of pi over 2 and the sine of pi over 2 is 1. Now we could go around and also pick the other points that have coordinates -1, 0 and 0, -1, and that would tell us the sine and cosine of pi and of 3 pi over 2. So we can fill in those coordinates as well. We have another row right here. So at 3 pi over 2, we have 0 and -1. And also at 2 pi, we are back where we started, so those coordinates are 1, 0. So we already know now the cosine of 0, pi over 2, pi, 3 pi over 2, and 2 pi, and the same with the sine. Now, the other ones are not that easy to just read off the graph, so I'm going to fill in the coordinates in the first quadrant. So the point at angle pi over 6 has coordinates square root of 3 over 2 and 1/2. And I'm going to do a little bit of cleanup because I need the space. And then the point at angle pi over 4 has coordinates square root of 2 over 2 and square root of 2 over 2. Note that sine and cosine are exactly the same. The x and y coordinates are exactly the same at pi over 4. And then at pi over 3, notice that the x and the y coordinates are exactly flipped from what it was at pi over 6. So if we're comparing the point at angle pi over 6 with a point at angle pi over 3, the x and the y coordinates are flipped, and so we have an x coordinate of 1/2 and a y coordinate of root 3 over 2. And now, just knowing those points, we can fill in the sine and cosine of the angles pi over 6, pi over 4, and pi over 3, because the x-coordinates of our 3 points give us the cosine. So we have pi over 3 over 2, pi over 2 over 2, and 1/2 for the cosine of those angles. And then we have 1/2 square root of 2 over 2 and square root of 3 over 2 for the sine of pi over 6, pi over 4, and pi over 3. Now, to fill in the rest of the unit circle, we can use the symmetry that's visible in our unit circle. So, for example, if I go straight across my unit circle from the point at pi over 6, I will get the coordinates of this point over here on the right. And notice that the x-coordinate is the negative of the x-coordinate that we had on the point on the right, and that the y-coordinate is the same. So I can fill in this point, for example, and then I can also figure out the associated angle. So what angle is that? This is, let's see how we get there. So my original one was in pi over 6, so I have pi over 6, but then I have another pi over 6, I have another pi over 6, I have another pi over 6, and another pi over 6. So I just went 1, 2, 3, 4, 5 angles that all had measure pi over 6. So this angle is in altogether 5 pi over 6. So I just figured out the sine and cosine of 5 pi over 6 and see that that's minus square root of 3 over 2, and the sine of 5 pi over 6 is 1/2. And in the same way, I can fill in all the other coordinate points and figure out what the cosine and sine of the associated angles are. So I can fill in my entire table, and here we see it completely filled in. So we have our unit circle, we have labeled all the points on the unit circle, and we use that to fill in values of the sine and the cosine function. So we can use that now to get a picture for what the graph looks like of these functions. So let's go back to what we did and see if we can graph what's going on right here. And you may want to punch some of these values into your calculator just for our use. The square root of 3 over 2 is approximately 0.866, and the square root of 2 over 2 is approximately 0.707. So let's graph our two functions. Let's start with the cosine function. I'm going to use red for cosine. So cosine of 0 is 1, and I'm just plotting my points. Then what else do I have? Cosine of pi over 2 was 0, and cosine of pi was minus 1. Cosine of 3 pi over 2 was 0 again, and the cosine of 2 pi was 1, back where we started. And then we filled in a few more values for in the first quadrant. So right here I have pi over 6, over here I have pi over 3, and in the middle is pi over 4 between those two. And we found square root of 3 over 2, which is approximately 0.866 right there. We have 0.707 about here, and then we have 1/2 about there. So we see these points, and if I graphed a few of the other ones, I would get minus 1/2, minus 0.707, minus 0.866, and so on. So it looks about like this. So my cosine function, I can connect the dots, and I get this wave-like shape. and it would continue somewhat like this. I could also do the figure out the values of negative input values, and you would see that the shape also continues in the same way for negative values, input values for the cosine function. Now for sine, we can do the same thing. The sine of 0 was 0, and then it was again 0 at pi, and at 2 pi it was equal to 1 at pi over 2 and equal to minus 1 at 3 pi over 2. And if I also plotted the other points, I would get a very, very similar wave. So I got 1/2 over here, I got 0.7. Oops, sorry, that is wrong. I actually have the same sine value as cosine value at pi over 4, and then I have 0.866 roughly over here. So my sine curve looks like this, and if I carefully draw it, it will have the same wave-like shape. And also true for negative input values. And we can see the complete graphs drawn right here. So this is more carefully done. And we see that cosine theta and sine theta have the same shape, and we can describe them in terms of period, amplitude, and midline. And we see they have the same midline of y equals 0. They have an amplitude of 1, and they have a period of 2 pi.